So, we will now, in the earlier steps that we had done, we had acceleration discontinuity at the intermediate points, and we are specifying velocity or we are using some other means. So, we have this technique in which we get continuous acceleration at the path points, okay, so that there is no visible jerk in the system, or jerk is limited. And so, this is called a spline. So, it is a spline fit. So, everybody uses splines. CAD, when you do CAD, there are lots of splines which are there. Essentially, when you have a set of points and you want to fit a curve with continuous acceleration, it is called a spline. Now, so what happens is, so we are talking about 2 points here and we want to pass a polynomial through it. So, we have 2 position constraints at the 2 end of it, and then I have time going around in the axis in the usual fashion. But now, instead of specifying the velocity, we only say that there has to be continuity of velocity and acceleration with the adjacent curves. So, I have one value which is equal to qk, the value of the curve at that time tk is known. So, I impose this constraint, but so this is one curve and this is the next curve, okay, polynomial. So, you write pi, Greek capital P, okay. So, you write the next curve. Now, these two values of these two curves at the same time tk must be the same, otherwise you will not have position continuity and you get this value. Second thing what you are saying is that the derivative must be the same, the acceleration must be the same. The only difference is for the position I already have this value qk. I do not know these two values for the derivative and the accelerations, but I am saying that they must be the same. Okay, so, this is the essential condition which I am writing. So, if you have n path points, then you will have, so this is 4 equations, this is 4 equations, and there are n minus 2 internal segments. So, you will get 4 n minus 2 equations for the internal points, and you get 6 equations for the endpoints, because for the endpoints slopes are known or something like that is there. So, this pi 0 t1 first derivative, second derivative at the first position and the final position are not variables, okay. These are imposed as initial and final velocities and acceleration. So, they are not variables in the problem, okay. Similarly, these pi 0 t1 and all are not variables, they are imposed on the problem, okay. Now, each one of these, so when I write a cubic polynomial here, so each polynomial will have 4 variables, okay. So, in the end you will end up with 4 n minus 2 equations in 4 n minus 1 unknowns, and you know immediately that you can find solutions, right, infinite number of solutions, okay. So, you can theoretically find a minimum norm and then you can find null space, 2 null space vectors, but that is not okay. So, one option is that if you just remove 2 equations which allow arbitrary assignment of the initial and final acceleration values, they are removed, okay. So, fine, I will not specify them. So, you remove those 2 equations, then you can solve for this. So, in the initial and final points you do not impose the acceleration, you say okay fine, I just impose velocities, but you must impose velocities because you are going to start from rest and finish at rest on the trajectory hopefully, unless you have a continuous trajectory, which is a separate issue. So, if you take a third order polynomial, then what is its second derivative? It is linear. So, the acceleration value will be constant throughout, right. So, you cannot then adjust the acceleration. So, now if you are connecting multiple points like this, so I have to adjust the acceleration here to make it continuous with this. Once I do that, it is constant for full length. So, I cannot adjust it here to take a assigned value. So, if I do that, then I have to use a fourth order polynomial, but then the number of variables will increase too many. Okay. So, there is a trick which you do is that you still use third order polynomials and you introduce two things which are called virtual points. Okay. So, what we do is when you have these points here, we just introduce 2 points in the middle where we say okay, so I need a polynomial here to here and a here to here, but I am not specifying the position of this. I just ensure that I just make sure that there is continuity of position, velocity and acceleration at those points, but I do not specify either the position or the velocity or the acceleration. Okay. If you do that, then you will see the number of equations and everything matches out and you can find out these n plus 1 cubic polynomials which result in the problem. Not getting into the details because it is not a method, well it is a reasonable method. So, what you do is in this thing you take n plus 2 time instants, okay, tk, and then conventionally you take t2 and tn plus 1 as the virtual points. So, this is the labeling, okay. Conventionally t2 and tn plus 1 are called, they are called the virtual points. So, then if you look at it carefully, you have 4 times n minus 2 equations of this type, okay. Okay. And so, these equations are for k is equal to 3 to n written for the n minus 2 intermediate path points. So, then you have these 6 additional equations for the initial and final points: position, velocity, acceleration, position, velocity, acceleration, you are specifying them. Okay. And then for the 2 virtual points we have 6 equations, and this is for k is equal to 2 and for k is equal to n plus 1, where I just say position is same, velocity is same, acceleration is same for the 2 polynomials and 2 sides of it.
Sir, is the second virtual point n plus 1 or n plus 2?
There are 2 of them.
Second virtual point.
No, k, the index k is equal to 2 n plus 1, 2 and n plus
1 is used for both the virtual point and the last point.
no, last point is n. You start from 1 to n points are given. So, n plus 1 is the index for the virtual point and 2 is the index for the virtual point.
So then what about the actual second point?
You do not label it 2. So, you label them 1, 3 and proceed like that.
Yeah, the actual points
Oh, so then it becomes n minus 1. No, so I am labeling them, let us see, there is a notation problem here. So, introduce 2, so I am now going from n to n plus 2. Oh, okay. Yeah, I am going to n plus 2. So, this is a notation problem throughout, I will have to fix this.
So the last point.
Yeah, it should be 2 and n plus 2. Okay. Unless okay, let us assume that, okay, so I have n minus 1 initial points. So, I am keeping 2 blank. So, once I have introduced the virtual point, once I have introduced the virtual point, do you get the question that he was asking? Initially I started by saying there are n points, right. So, if I have n points and I introduce a point at 2, a virtual point at 2, then the label of the nth point should become n plus 1 now. So, then the virtual point will become n plus 2. So, let us assume now that what we are doing is that once I introduce a virtual point, so if I actually had n minus 1 points, I label them 1, 3, 2 n. Okay. So, what I get actually is different. So, I have actually n minus 1 specified points for which I know qk. Okay. So, I have n minus 1 points for which I know qk. So, if I have n minus such points, then I will get n minus 2 equations of this type. So, I have exactly 4n plus 1 equations in 4n plus 1 unknowns, and so these are the coefficients of the n plus 1 cubic polynomials. Life is simple, right. So, you write the equations, so you get this 4n plus 1 by 4n plus 1 matrix and you invert it, right, and you are home.
Now,
Or you can use, I mean, whatever, you use Cramer's rule, you invert it, same thing. You know that this is difficult. There are all kinds of problems with this, including pivoting and all of the issues. Have you ever inverted a large matrix? No? Not in the maths course? Really? What is the largest matrix you have inverted? Huh? 4, 4, that too in this course, huh? Okay, so you will do it. You can try and invert it and see what you get as the answer. And so there are lots of problems with it, and it is very sensitive, you know, numerically it's unstable, trying to generate so many coefficients together. Now, so what we will do is we will look for a better solution than this, than inverting this very large matrix. Okay. So what we do is that if you know that the polynomial is a cubic, then its second derivative, so this is the cubic pi kt, so its second derivative pi kt of second derivative of pi kt, pi double dot kt, it is a linear function of time. So a linear function has two parameters. So what we are doing is we are writing that linear function as a function of the value at tk and the value at tk plus 1. Okay. So this is the expression for it, and this is we can write for the 1 to n plus 1 and where delta k is defined as time interval between k plus 1 and tk. So I have just defined the second derivative as a linear function of time. Now if you just integrate that twice, then you get this big expression which contains this, see this tk plus 1 minus t is essentially a variable which is a variable which is 0 within the at the start of the segment and goes to some value at the end of the segment, and this is kind of normalized by using delta tk, but not fully. So if you look at this term, this tk plus 1 minus t, right. So in that inside that segment this goes, and this is, if this is divided by delta tk, this goes from 0 to 1 within the segment. Okay, it's a kind of like a normalization factor which has been put in there. Now the only advantage is that when you write the generic polynomial, it is just ax cube plus, okay, in this case at cube plus bt squared. So a, b, c, d are all to be determined as coefficients. What I have changed here is that I have landed up with these 4 unknowns, and you know immediately that these two are actually not unknowns, but these are specifications. Do you see that? Because this pi k tk essentially has to be qk, and this is also known. So 2 of the coefficients are of this polynomial are, I mean 2 of the parameters are immediately known from the input data, I do not have to compute them. Okay. So there is a significant reduction in already in the matrix size. So instead of 4 n plus 1 or 4 n minus 1, I am already dealing with 2 n minus 1. Okay, I have just reduced it by 2 huge steps just by using this formulation. There is a small point which I want to make out. See, there are 2 terms here, like if you say pi k t, this is the polynomial, right? on the other hand, moment I say Tk, that is a value at a point Tk. Okay, so that is a not a variable. So just keep this in mind when we are going through this presentation. Okay. So is this point clear? Why am I going into this formulation? So I am just reducing the number of orders, but without computing I am shoving those values in. So that's so n variables qk for k is equal to 2 to n plus 1 input through pi k tk. Yeah.
So in the previous equation, do we know delta Tk?
Oh yeah, because you are giving a trajectory.
So where the equations that we are providing does not include the time interval from reaching to n from k to k.
No, it has. I am assuming that you are specifying a trajectory. Is that clear to everybody? That I am giving pairs qt, qk, tk, qk plus 1, tk plus 1. I am dealing with trajectories, not paths.
Sir, and that velocity and acceleration should be continuous is a constraint.
I am saying that it should be continuous. I am not specifying them except at the ends. I am saying rest I really do not care, you just make sure that you do not have discontinuities of velocities and acceleration. So we are setting continuity. Okay, so some values are coupled together inside, so that is another equation. And so essentially you know the values of the points in the beginning and the end, so this essentially reduces down to 2 times n plus 2. Okay. Now here is the interesting one. If you look at this expression and I take a derivative, right. So derivative will involve functions of again pi k double dot at tk and the values. The values of the second derivative and values of the function itself. It will not have any other terms, right. Now, so in the beginning and end, right, so you can write the derivative essentially as a functions of the values of the second derivatives at the end and nothing else. So they are eliminated. So you are finally left with 2 n plus 1 unknowns in this problem. So then you write the continuity of acceleration equation, that will reduce, so half the variables are gone, and then you use q dot double I and q dot initial and q dot final are given, unknown will reduce to n. So finally you get n equations in n unknown, which are just the continuity equations in this form. Okay. So now if come down to n equations in n unknown that we have to solve for, the rest you get by back substitutions and things like that. Now the n by n matrix looks like this, and this is then multiplied, the only parameters which are lifting here is this, we are solving for these, and this then has to be equal to b. So we can compute a and b. Now if you look at the structure, the way I am getting these equations is that if I come back to this equation, or rather I come back to first to this equation. So I get an equation of derivative of this with respect to this. I get this by taking the derivative of this equation with respect to time. So in any of these equations I have already eliminated the pi k tk plus 1 term. So I have terms of this pi dot k tk, pi dot k tk plus 1, okay, 2. So if I take 2 adjacent ones, I will have at the most 3 terms. These 2 are common and 2 more in the middle. So what that will end up doing is that it will give me a structure like this, where at the most 3 of these terms are used in every row. So, 3 of the second derivative terms are involved in every row. So, this is called a tridiagonal matrix. Okay. So, it is essentially a diagonal matrix with a band of 3 in there, and there is something called so B is known and A is essentially, you can show that it is not singular, tridiagonal band structure. And if you look at this matrix is same for all the joints and it only depends on time interval delta k, nothing else. So, it is scalable thing. So, all of that is very nice. So, the only thing it depends on is how many points do you have in the middle, that is it. And then you should then go to Wikipedia and find out about tridiagonal matrix algorithms, and so there is a simpler method than Gauss elimination, okay, to solve the tridiagonal matrices. So, essentially you have this form. So, ai xi minus 1 bi xi, so 3 terms is equal to di, and you can get the solution in order of n operations instead of order of n cube, which you require in Gaussian elimination. Okay. And if you look at the solution, so using these two you can eliminate using this equation, right. Since this is known, I can say I can write the expression for pi 2 double dot, that polynomial at T2 in terms of pi 2 double dot at T3. In this equation, when I substitute that, okay, so I have eliminated this, so I will get an expression for pi double dot 3 in terms of pi double dot 4. As I keep marching, when I come to the last one, since I have already eliminated this as a variable, so I will get a expression for pi double dot n plus 1. So, then I go back again substituting everything back here, and then when I go back a second pass, I have solved everything. Okay. So, this is the basically 2 pass tridiagonal matrix algorithm. It has got nothing to do with robotics. So, I am not getting into the detail. You can go into Wikipedia or you can go into any book in linear algebra, they will have more. And if people have done CFD, you know what is CFD, right? Computational fluid dynamics, you write difference equations, you also get tridiagonal matrices. Okay. So, standard procedure for solving it. And so, this is also known as the Thomas algorithm, okay, named after Levin Thomas. So, it is an interesting character, you should look him up also. And so, this is what finally happens. So, if you look at this curve, so there are 2 curves here. So, this is initial point 1, label 3, label 4, label 5. Considering 2 cases, one in which the virtual points are here and here, and one in which the virtual points are here and here. Okay. Now, depending on where you, so this is the time axis. So, the virtual point is specified in the time axis, but it is not specified in the position axis. Okay. So, if I specify this here, then I get this curve, and specify this here, I get the other curve. Now, depending on which one you do, the velocity profile changes and the accelerations change, right. And if you look at it carefully, this acceleration will be preferred less compared to this acceleration profile. Okay. So, the solid one corresponds to this one, the cross, and the dotted one corresponds to the star. you know immediately, because there will be a cubic polynomial between this and this, so the acceleration will be constant over that interval. So, in case you lose out, well, I did not put it here because I just want to point this out. So, I know that this one is the one corresponding to the cross, and the dotted one is the one corresponding to the star. Now, if you compare the accelerations, this dotted one has higher accelerations. Okay. So, it is a less preferred one, because to get higher acceleration you need larger motor torques for this problem, which is not desirable. So, your motor torques are not determined only by your final payload, but you know how quickly you want to move things, and what is interpolation which you use. So, everything you know demands motor torque, so it will add to it. So, what is the difference between these two cases is, in the first one we had T2 is equal to 0.5 and 0.5, 4.5, 1.5 and 3.5. Okay. And the basic rule of thumb is, if you move the virtual points closer to the intermediate points, then these accelerations increase. So, further you move them away from the intermediate points, these accelerations get lowered, but there will be a minimum acceleration which you are still left with, you can't help it. So, ideally you should be able to, well, if you work a little harder, then what I have done so far, you should be able to figure out which position minimizes the overall acceleration also, not very difficult to compute, you can do that. So, if somebody is paying you a lakh a month to sit and program a new robot, so that is when you do these things. So, but quite obviously you can do that. If I tell you that depending on where I move this, if the acceleration changes and you know you want to minimize it, you write another equation and you will just minimize that and solve it. The polynomial equations, not very difficult, but somebody has to do it for you, or somebody has to do it for the person who uses the robot on the in the workplace. So, that cannot be done by the programmer there. So, is this clear? So, it is quick because you know everything about polynomials, right. So, what did we do? We took a system of 4 n minus 1 equations and we systematically reduced it to n equations and n unknowns, number 1. Not only that, it came out to be a tridiagonal thing. So, it is very simple, you do a one pass and it becomes a bidiagonal thing, and then you do the other pass and you get the solution. Okay. And that is very efficient, and so this is also tells you about splines, how splines are worked. Any questions? No, that's a wonderful class. Okay, now some people say even this is too complicated. Was it complicated? No, nothing is complicated for this class, right? So, so if you look at it carefully, what is my issue? The issue is that I want smooth transitions, I do not want jerks. So, the proposal is very simple. If I have to go from Q2 to Q3, I can always draw the straight line, and then going from the next point to next I can draw another straight line. Only problem is that at the junction I will have discontinuity of both velocity and accelerations. So, then I say very simple, what I do is I do that, then I take this time interval delta T2 prime on both sides of the point, and as I find wherever this intersects the line from here to here, I will put in a parabolic blend. So, that takes care of my velocity discontinuity at that point. You got the idea? So, straight line here, I just take two equal time intervals from here to here, else I will draw a parabola. Okay. So, there are two things here, one is this delta T2 going from Q2 to Q3, and then you specify delta T2 prime, which is a time interval around Q2, around Q2 T2, over which I will do the blend. So, it is a very simple algebra. So, you interpolate with linear segments, okay. We use blend using parabolic profile around Tk. So, you have a series of linear and quadratic polynomials. We live with the discontinuity of second derivative, so it is not a spline, and so there is a constant acceleration. So, basically there is a, in the linear portion there is a constant velocity, and then we have a constant acceleration in the parabolic blend. So, these are two parameters which are there. So, you simply set up these two equations defining them, it is very simple. Okay. So, velocity, acceleration, intermediate points are, there is nothing to do about it, you know the values, just set it up. You define q dot k minus 1 comma k over an interval, and using this definition you define the accelerations over the blend. It is extremely simple, no matrices, and you can do it sequentially. So, join 2 points, join the next point, take this, blend this, go to the next one. So, it is just a single sweep pass and you have it. In fact, you can do it on the fly also. You just need to be one step ahead of where your robot is, and you can keep on giving it problems. You do not have to solve the whole thing first and then start moving the robot. Now, the only catch is, I hope you noticed, did you notice that the curve is not going through Q2? That is not a drawing error. Let us compare. Going through, not going through. Okay. So, so we are not going through the specified points except at the ends. Question does not matter. Yes and no. So, there is a slight deviation, and if you reduce the delta T prime, okay, the area around this where if you reduce this area, then it will get closer and closer to Q2. The more you increase the area, the further it will go, but your acceleration requirement there will reduce. And so, these points which we specified, they are called via points. So, the basic approach is this, that I know I want to start from here, I want to finish here. So, these two things are fairly well determined, that okay, I should show it in this plane. I know I want to start from here, I want to finish here. So, and I want to, so this is pretty much known. Now, then I say okay, you go through this area, question is how accurately do I know this? If I, like I said, if it is a circle, then you can write an equation for that, but quite often we do not know, we say okay, generally do not be the object here, there is an object here, so it is okay, you go through here. So, quite often the internal points are not very stringent, right, and it is not that it just goes away, out of the way, and if you put in more points in that area, then it will get better and better. We know these things. So, if you want more accuracy, you can just pump in couple of more points and look at this simplification which is obtained, because I am not inverting any matrix at all. I can do this on the fly. So, if you change the path at any time, I can quickly compute, I just need to be 2 steps ahead of the robot and I am in business. So, this is the elegance of this method using via points. The only catch is we need to treat the first and last segments separately, okay, because we want to start up and end at the rest points. So, what you end up doing is that you specify and then you want start and end So, you want to specify them. So, what you do is that your blending process, so we will get to that. So, what you are now doing is, in the blending, in the end we have a slope and that slope becomes 0. In all the intermediate points we are calculating the slope from the next segment, previous segment and the next segment. In this case we are saying the slope after that becomes 0, right. But the slope will not become 0 at that point at which I specified, it will not become 0 at Tf. Let us go back to this. See the slope, this slope merges and becomes this slope after the time delta t prime by 2. It does not become 0 here. So, in the end also I will have a similar problem. Okay. So, what will happen is, if I have to wait for it to slow down, right. So, I have to just give it a little bit more time, and the time is essentially delta t1 prime by 2. So, you go to add delta t1 prime by 2 and then add delta t2 prime by 2, and then you have the final time interval. So, this is very simple, you just calculate these values of q dot k minus 1 k and q k double dot from the given profile, and linear parabola polynomial parabolic is generated. So, for your upcoming assignment this is what are targeted. You will be implementing this after you have done with this series. So, let us have a see. So, use two time intervals delta prime tk and equal to 0.2 and 0.6. Okay. So, this is the shorter time interval, so it gets closer to the wire point. The solid one on the other hand has, you can see already here that, see the final velocities that it reaches are determined simply by these lines. So, that is the same in both cases, but you can see that the solid line is getting to that velocity in a much smaller time interval in all cases. So, the accelerations are much higher. So, this is the compromise which you will have to live with. Okay. In this process, but it is a so this is the summary of that. So, with tk prime delta tk prime 0.2, qt gets closer to wire points. So, you would expect more torque demands from the motor, which is not good, and we are essentially applying trapezoidal velocity profile law to the interpolation problem, and the only thing that is doing is that instead of stopping at the intermediate points, we are just going smoothly through it. So, instead of saying, okay, if you are given 6 points, you start here, stop here, start here, stop here, start, stop, that is what just doing the single step trapezoidal thing would have done. This is quite simple and does not require matrix inversion. There is one more method which we need to look at, which is even simpler. So, what we are trying to do here is, so we just consider one intermediate point. Okay, so, you start from here, and so if you did start stop trapezoidal, you would go up, come down, get to 0 velocity, then you would start again and come down again. Okay, you do this. Now, instead of doing this, we say fine, what you end up doing is you take a time interval and then you make, instead of going down here, you make the velocity be a mix of this and this, and you transit from this velocity to this velocity. You join it on this curve. So what you are doing is you start generating this, you knowing that I am going to come down and then I am going to rise, you say this is stupid. Now why should I lower the velocity when I am going to rise again? Get it down to 0, you say okay fine, I know how I am going to rise, so I am going to do a mixing of these two, just a straight away average of this. So this is the method, and so what this does in this process is, so you start with the trapezoid, so this is a parabolic profile, it goes here, now instead of coming down here and getting 0 velocity, it just kind of passes over this and goes kind of parallel to this path, and then finally you reach the position at here a little ahead of time because you did not slow down here, and you attain that velocity using this method. So it's a very simple this thing, the only thing is when do you do the time anticipation, what is the value for it, and if you don't do it right then you are going to be in a little bit of a problem, but you can take care of all the cases, because as you increase the time interval, so instead of going from here to here, you might go from here to here, or you might go from here to here, somewhere here directly on the slope. So you just have to play around with it to figure out what is the right parameter. So this is another method which is also there, in which you don't even compute a quadratic, just find the average and find out a delta t and just shove it into the routine and just follow the trajectory. So summary, we have gone through this host of methods, right, starting with point to point, then you put in intermediate points, we derived everything with velocity continuity and specification at the ends. Then we said no, we want acceleration also. So then we realized we got to mess around with it a little bit because the equations are too complicated. So with lot of messing around, introducing the pseudo points, virtual points, then we landed up with a spline where we have velocity and acceleration continuity. Then we said, yeah, all this is very nice, but I just don't want to invert matrices. I don't want to compute the whole path in one go. That's the second thing, So then you came out with the blending method. So we did two blending methods, one of them we actually blend properly so that I have velocity and acceleration continuity across the via points. And then we looked at this last method where you don't even do a quadratic blending, you simply take the average of the velocity values and just patch it together. So it all depends on what is the agility of your system. So if you have direct drive motors, if your robot is very light and does a lot of dynamics, then you might want to compute the spline. Okay, but this means that you have to compute everything in advance and then go through, because if you are going here and then says, oh, instead of going there you go here, right, then the whole path changes, because the spline for this here will be very different from the spline from here to here. You can try it out because all these packages have splines. So you can put in points and then you see if you change this, what changes at the back, everything changes.